This limit, it is going to wind up being a Hopital rule one, but it isn't quite apparent right away. Usually we want it in a 0 over 0 or infinity over infinity form. So as this thing approaches infinity, I get 4 times infinity, right? So it goes infinity. This kind of gives me an infinity times 1 over x. Well, I'm doing tan of 1 over x, so I got to look at the 1 over x first. The 1 over x goes to 0 because as x goes to infinity on that, it's a horizontal asymptote. So this goes to 0, which means that I'm taking something that is the tan of 0, right? And the tan of 0 is 0, right? So what I sort of have here is a form of infinity times 0, which we can often evaluate using Hopital's rule. So there are lots of techniques for this, or there are lots of techniques for Hopital's rule, and you can actually do this particular problem in a couple ways. But the easiest way is to actually introduce a new variable and say let h, my new variable, be 1 over x, and then if I solve for x, I get x equals 1 over h. And I'm going to replace these x's here with h's, or 8 forms of h's, right? So what you should notice is that I'm looking at x as x goes to infinity, right? So as x goes to infinity, what happens to this expression? Because that'll tell me what happens to h. So as x goes to infinity, well, I know that 1 over x, which is h, goes to 0 because of 1 over x graph. So as x goes to infinity, h winds up going to 0. So what I'm going to do is change this limit over on the left side to have h's instead of x's. So here I've got 4 times x, so I'm going to have 4 times 1 over h. And here I've got tan of 1 over x, so I'm going to get tan of h. And then for this thing, I'm looking at the limit as x goes to infinity, and we just said that as x goes to infinity, h goes to 0. So I'm going to replace that with an h goes to 0. So it's going to look like this. Limit as h approaches 0 of 4 times 1 over h times tan of h. Well, that could be rewritten as limit as h approaches 0 of 4 tan h over h. Now, I'm looking as h goes to 0, so I'm going to get 4 times tan of 0, which is evaluatable. That gives me 0. And then as h goes to 0, the bottom, which is just h, also goes to 0. So this thing goes to 0 over 0, which means that I can now use Hopital's rule. So I am going to hop it, which means that I'm now looking at the limit as h approaches 0, fraction bar. And Hopital's rule lets me take the derivative of this, and the derivative of this, right? The derivative of this, and that just goes in the top. And the derivative of this, it just goes in the bottom. So I'm not doing quotient rule, I'm just deriving the top and deriving the bottom individually. So for the first one, derivative of tan secant squared. So I get 4 secant squared of h. And then in the bottom, the derivative of h is just 1. So this is now something for which I can plug h equal to 0 in, right? So I've used that Hopital's rule, and now it's evaluatable. So as h goes to 0, well, let's rewrite this. So this is equal to the limit as h approaches 0 of 4 over cosine squared h, and I'm just using the relationship between secant and cosine. So now the question is, what's cosine of 0? I think about the unit circle. I know it's the x-coordinate at 0, and that is equal to 1, right? So I'm looking at 4 over, when I plug that into here, I get cosine squared of, or I get cosine squared, I get this value, which is cosine squared. So I get 4 over 1 squared, which is just 4. And that's my answer.